All right, let's work through Pathways 3.12 from your book. This is a really important type of introductory problem involving interconversions between mass in grams, number of moles, and number of atoms or molecules. Okay, so this is meant to demonstrate the concepts, and you can kind of take this, learn about it, and run with it from here to more complicated problems. But these are all really the same. I hate to say they're too much more complicated. You just have to understand the concept and you got it down. So part A wants us to compute the mass in grams of a sample of zinc, which is 0.346 moles. When you're working this type of problem, it turns out that it's very much a unit conversion problem, okay? Very, very similar to unit conversion. Essentially is. We're converting between moles, mass, molecules, atoms, whatever. Here, we want to know the mass, but we're given a certain quantity in moles, 0.346 moles of zinc. We can treat it like a unit conversion by multiplying by our conversion factor again. And remember back from chapter 1 when we did this, your undesirable units were what? Down here in the denominator. And your desirable units were up in the numerator. Here, that's going to be grams of zinc. We've got to put some numbers in here on the top and the bottom of the fraction. Remember, it has to be physically equivalent. The two that we put here and here, physically the same, just different units of measure. Let me ask you this. If I asked you what is the mass of 1 mole of zinc, what would you say and how could you figure that out? Hopefully, by this point, you would know that the atomic mass listed in the periodic table of the element for zinc corresponds to the mass of 1 mole of zinc atoms in grams. That number, which is for zinc atomic number 30, is 65.38. .38 grams per 1 mole of zinc. So you see we've got all the things that we need now. The mole units cancel. We convert to grams. We just need to punch the numbers in on our calculator. Turns out if you do that, you get about 22.62 grams of zinc. You're done. So that's part A. There's another portion to this problem. Let's consider that. In part B, we're asked for the number of fluorine atoms in 2.62 moles of F2. So we asked how many, specifically how many moles. Nope, we're asked the number of fluorine atoms. So how many fluorine atoms? An actual count. Okay? Not how many moles, actually how many if we were to count them in this amount of fluorine gas, F2. This, of course, be a gas, a very, very reactive gas. So how are we going to approach this? Well, again, it's nothing more than a unit conversion. So what do we know about moles and the copies of number of molecules or atoms of something? Well, we know this Avogadro's number, right? We can use that as a conversion factor for us here, okay? And we know that moles are just a counting unit. So I could set up my conversion factor so that the moles of F2 cancel out. And I could start counting molecules of F2. Now, we know that Avogadro's number, 6.023 times 10 to the 23rd, tells us how many molecules are in 1 mole. So the mole units cancel, and if I do this math, I've converted to molecules or particles of F2, which is the diatomic version of fluorine gas. You see that? So just to finish this off, let's report the number that I would get. If I check my calculator, it looks like it's 1.578 times 10 to the 24th. 1.578 times 10 to the 24th. I believe what I'm showing here, okay? Yeah, for 2.62 moles, okay? Now where do we go from here? Is that our final answer? Well, what is this? And what do we want, more importantly, right? What I've just computed, and I want you to work on having a really clear mental picture of this before we go on. What I just computed is the number of molecules of F2, or fluorine gas. This is the diatomic version. I had this many moles of that diatomic version, and because this defines how many moles, or this number defines what a mole is, basically, I have computed the number of molecules of F2. But notice that in the problem, I'm asked how many atoms of fluorine. Take a second to convince yourself of this, but the number of atoms of fluorine is not equivalent to the number of molecules of F2. Now there might be a relationship between the two. They might scale together, but it's not the same thing. And again, this is where reading the problem becomes very, very important. Because if you just stopped here, unfortunately that would be an incorrect answer. We have another step, another conversion to carry out. So of course what I need to do is take the information that I've already learned about the fact that I have this many molecules, and use another conversion factor. And of course, what I want to convert to is my final answer, which is going to be the atoms of fluorine. Well, how can I do that? Well, for every one molecule of the diatomic version, that is the F2, how many atoms are involved? Isn't it 2? By definition? Because it's F2. Every single molecule of F2 has 2 fluorines that are bonded together. 2 fluorine atoms, right? So it makes sense then if I'm going to calculate or figure out how many atoms of fluorine total I've got, well, I've got twice as many atoms as molecules. So I just take that number and multiply by 2, and I have my final answer. Now if I do that, it looks like I end up with 3.156 times 10 to the 24th atoms of fluorine. That's about how many atoms I've got in a 2.62 mole sample of F2 gas, okay? So again, you can see how we went from moles to actual number of particles. We could compute how many molecules of fluorine we've got, the F2 version. We could compute how many atoms of fluorine atoms are present. For moles, we could also compute grams by multiplying by the molar mass of F2. So we can perform all these interconversions, and that is a big, big, big goal here of Chapter 3, that you're able to do that. All right, let's move on. Part C. Part C asks us about the number of calcium atoms in a 28.5 gram sample. So we've got 28.5 grams of calcium. We want to know how many atoms of calcium is present in the sample. So when you're going to start one of these problems, again, you need to think about your strategy first, right? It's always an interconversion between mass, moles, atoms, molecules. Got to think about a strategy. Very frequently, you will proceed through mole units, because remember, a mole unit is our counting unit. So can I convert this to number of moles of calcium? I think I can. Because on my periodic table of the elements, if I look for the box for calcium, it tells me that 40.08 grams of calcium is equivalent to 1 mole of calcium. Now I don't have 40 grams, I've got less than that. So I'm going to have less than a mole of calcium, slightly less than a mole. And in fact, if I do the calculation on that, I end up with 0.711 mole of calcium. That's just based on mass, right? To get to 1 mole, I need to have this. I don't have that much. I got less than it. How much do I have? Do the division and find out, right? But the beauty of this is now that I know I've got this many moles of calcium, I can do one additional computation. To go to calcium atoms. So I set up my mathematics. I want to get rid of the mole units of calcium. What's the key value here? Well, whenever I'm counting particles, whether that be atoms or molecules, I can remember that 6.023 times 10 to the 23rd power is my key number. That's my Avogadro's number. So 6.023 times 10 to the 23rd atoms make up a mole of calcium. If I have this many moles, I can surely compute how many calcium atoms I've got just by multiplication, right? And if I do that, I've got about 4.282 times 10 to the 23rd. That's how many calcium atoms that I've got. So this many calcium atoms correspond to 0.711 moles of calcium. This many grams correspond to this many moles of calcium. This many grams of calcium also corresponds to this count of calcium atoms, 4.28 times 10 to the 23rd calcium atoms. So it's all consistent. It's just different units for tracking the amount of material that's present.